All right, so now in this video, let's talk about some of the remaining losses that occur in the transformer. We've already talked about the copper losses and the leakage current losses. Refer to the other videos if you want to learn more. So if you connect the secondary side, let's say a load, and we want to know what would be the secondary side current if we know the I supply, let's say this is I supply, okay, or let's say I primary, I guess, I primary, what will be my I secondary, right? So the relationship is fairly simple that I set, let's assume this is a 230 kV to 25 kV transformer. So I secondary is equal to um, what I supply. But since this is a step down transformer in voltage, the current will be higher, right? So 230 kV divided by 25 kV, like that. So let's say if I supply was 1 amps, 230 divided by 25 kV will be 9.2. So your answer will be I secondary will be 9.2 amps. It's fairly high as compared to the I supply. But in reality, what you would notice is that when you apply, after if you were to apply a 1 amp and you were expecting a 9.2 amp on the secondary, you won't necessarily get a 9.2 amps. You would actually get something a little bit less than 9.2. I'm just going to make up a number just for the sake of an example. Let's assume you get an 8 amp, okay, instead. Okay, so what happened to you were going to get a 9.2 amps, but you're now getting an 8 amps. So what happened to the 1 amp? Where is it being utilized? So let's talk about that because those are also losses. So essentially, when you supply the voltage over here for the and again, keep in mind that there is an insulation between this red coil that I'm showing and the core. So the current is not actually coming directly. The I primary is not directly coming into the core, but rather the I primary is just staying in the red coil, and then the magnetic fields are being induced. So when the magnetic fields are being induced in that when the magnetic fields are being induced in the core itself is also iron, right? So it can also have some sort of circulating currents, and we call them eddy currents. I'm just going to use orange color, and like this. And so some of that current that the I primary would have been, the I secondary should have been just the ratio between the two, but no, we've actually got some losses in between. The losses are that some of the current is now being induced in the core, and those are called eddy current losses because you got changing the negative magnetic fields. The core material itself is also conductive, so it will create some sort of circulating currents, and we call them eddy currents. So I'm just gonna show them because these current create resistive losses. So I'm just going to show them as resistor, and I'm just going to call them R eddy for 1 sec right here. Now, because this magnetic field is set up, right, that also takes some sort of a current as well. So I'm just going to represent that as, this is in purple. So I'm just going to show it in purple like this. Because this is a magnetic field, the useful magnetic field, I am just going to show it like this as an inductor, like that. Now, another thing is that the supply voltage, is changing in nature or alternating in nature. So your magnetic fields are kind of changing direction in this core each time. So there's something called so for the dipoles to line up, and then let's say in one cycle they're south to north, and then in another cycle they are, let's say, like that, right? So for the dipoles to flip back and forth, it takes some sort of an energy. Those are called hysteresis losses. I'm just going to show them with with the blue color here, and they're also resistive losses, or create heat. So I'm just going to show them as R hysteresis like that. Okay. And hysteresis losses again is associated. You've probably seen this curve quite a bit. Where it kind of goes like this, like that, like this, like that, right? So the idea is that, let's say if this is my current, let's say this is my magnetic field. This is generally called H. or like that. But really, as you increase the current, so I always think of it like a current at the on my x-axis, where when you're increasing the current, the magnetic fields are being created. But as the current reverses the direction, so you could see when you are at zero current and going in that direction, your flux is still in the positive direction right here, like that. So your dipoles are still facing in that direction. So from here to here, for you to flip that dipole, uh, to see the other way around, or to flip the other way around, it takes some sort of an extra energy, and that's called hysteresis losses. Now this gets a little bit more fairly complicated into when you're performing transformer energization studies and whatnot. But right now, let's keep things simple. I just want you to have an idea that there is some sort of losses associated with flipping of the dipoles that are called hysteresis losses. There are some losses that are associated with the currents or circulating currents in the core. Generally, I'm showing this core to be, quite thick, but in reality, there's a bunch of these plates that are just kind of glued together to make this core. They're iron plates. They're very thin. So if there's not much of a surface area at the top, like and have these edges, then you can really reduce the circulating current, because they need a surface area to circulate, I guess, right? So but they do exist. So our eddies are resistive losses associated with eddy currents, resistive losses associated with hysteresis that occur due to the dipoles flipping in every cycle. And then we're showing some of the current that was being utilized to create the useful magnetic field. Now, all of that current, a lot of the time, right here, so that loss right there, right here, is generally called I naught, or it's also called I no load current. And there is actually a test that's performed, and in that test, what's done by the vendors is that they just basically keep the secondary side open, and then they apply the supply voltage, and they basically make some measurements. And then what the measurements are, if they see any sort of a current, they measure that current and they call it I no load current, because there is no load on the secondary side, but you still have some current which is flowing, which they then measure with, let's say, an amp meter per se, right? And then also they've got, similarly, what we talked about before, that there's a watt meter as well that's measuring the wattage, or the active power consumption, and then that active power consumption will then tell you the resistive losses. So if I were to just kind of like make it a little bit simpler and draw it out again, we've got the voltage, and then we got the watt meter, okay, and let's say I've got an amp meter, like that, right? And now I can and then this is open over here on this side. This right here, this setup is called no load test, okay, like that. And that's actually performed, and it will give you two values, and it will give you in summary, it will give you basically an I naught value, okay, which is also roughly I magnetization, is the current that's needed to create set up the magnetic fields, or I magnetization. And then it also gives you the no load losses. These are also sometimes called core losses, because remember the copper and the leakage did occur somewhat in, I guess you could say, in the core, but the leakage was the magnetic fields that left the core. And then the copper losses, of course, are happening in the copper. So the no load losses, because the R eddies are happening in the core, the hysteresis are happening because of the core, you call them core losses. And then they are made up of both the R eddy plus the R hysteresis, right? And sometimes when you read the manufacturer, they would just say, okay, you know what, both of these losses are, let's say, they'll just say, let's say, 70 watts or something like that, right? And then for magnetization, they will say, in percentage, they will say, like, this is like 1%. And then that's just the 1% of I rated on the primary side. Generally, that's what happens. And then the R eddy plus the R hysteresis, let's say, are 70 watts. So for us to be able to put that in Pscad, what you do is 70 watts divided by generally the rating. Let's say this, in this case, let's say this is a 100 MVA transformer. Let's assume that for 1 sec. So then you would do 100 MVA, and then you would come up with that per unit value, right? And then in the next video, I can kind of I can tell you some realistic values from an actual test, and then we can put them in a Pscad. But now you have a bit of an idea of what an R eddy is, R hysteresis, and then the magnetization current, and how they kind of relate to the losses in the transformer. See you in the next video.